Thank you very much for the introduction, and I'd like to thank organizers for the invitation. This is my second time in Montreal, and I'm very glad to be back here. So I'd like to talk about the 4D2D duality. In my talk, I loosely identify. Do you see the pointer? Oh, so what do I have to do?
Usually works.
It works, but not on the screen.
Just this one. Yeah.
This?
No, this one.
Well, this is just a
He wants the pointer.
pointer.
Oh, the pointer, it won't work on the TV.
Okay. Okay, so I loosely identify vertex algebra and vertex operator algebras. These are some algebraic system which gives rigorous algebraic framework for two-dimensional chiral conformal field theory, whatever it is. And because it's originally introduced by VOAs as algebraic framework for two-dimensional conformal field theories, it was not originally expected that the vertex operator algebra has anything to do with higher dimensional quantum field theory. However, things changed completely quite recently, which actually goes back to Nakajima's work in 1994. And this recent discovery is that the vertex operator algebras appear in higher dimensional quantum field theories as well, in fact, in several ways. So this is very nice because there's no mathematical definition for the moment for the quantum field theory, which has dimension higher than 2. So knowing anything about vertex operator algebra appearing in such theory helps us to understand this mysterious quantum field theory. And conversely, such a new connection gives us some new insights for a representation theory for vertex operator algebras. And this is something I'd like to talk about today. And so I will not talk about many connections with higher dimensional quantum field theories, but I just talk about one connection, which is a 4D2D duality discovered by these people, Beem et al. So what they did was that they constructed a map or functor from a category, the category of 4-dimensional n equals to superconformal field theory, whatever it is, to the category of vertex operator algebras, which we identify with the category of 2-dimensional conformal field theories. So originally, this map or functor was designed to do the following. So there's an important invariant called the Schur index in 4-dimensional theory, which is certain Q series. And if you use this map, you can compute this Q series as character of the corresponding vertex operator algebra. So this is nice because in 4-dimensional theory, Hilbert space is not a irreducible representation of a big algebra. It's defined as a direct sum of a finite dimensional representation of small superconformal algebras. So there's no big algebra which controls a Hilbert space. But in vertex operator algebras, the Hilbert space is a irreducible representation of this vertex operator algebra. So you can use the representation theory of VOA to compute this important invariant. And let me show some property of this functor. So one property is that there is a notion of central charge in 2D and 4D in both cases, which takes a value, which takes positive value for unitary theory. the relation of central charge of 2-dimension and 4-dimension is given by this. And because there's minus sign there, if you start with a unitary theory, which always holds for physical theory, you end up with non-unitary theory. So a vertex operator algebra appearing from higher 4-dimensional theory is never unitary. So in particular, this map is not surjective. And this map is defined as certain dimensional reduction. So it's natural to think that this map loses a lot of information of the 4-dimensional theory, but in fact, it's now expected that this map should be injective. So in other words, corresponding vertex operator algebra is a complete invariant of the 4-dimensional theory. So this is extremely exciting because, as I said, 4-dimensional theory is not mathematically defined. But if you use this map, we hope to be able to go back from vertex operator algebra to this mysterious world of 4-dimensional theory. Okay, so but then if you really believe that this is complete invariant, then you should be able to recover many invariant, not just a sugar index, because 4-dimensional theory is a super rich theory and has several interesting mathematical invariants or observables in physical terms. And one of them is so-called Higgs branch, which is a hyperkähler cone. So it's a geometric invariant attached to 4-dimensional theory. So if you believe the previous statement, you should be able to recover this geometric invariant from vertex operator algebra, which is purely algebraic object. And in fact, it's conjectured by Beem and Rastelli that you should always recover Higgs branch of 4-dimensional theory as a so-called associated variety of a vertex operator algebra. Here, I don't have time to define associated variety of vertex operator algebra, but I'll explain an example to give you some ideas. But associated variety of a vertex operator algebra is a certain affine Poisson variety that was introduced as analog of the associated variety of primitive ideas of UG. So, yes?
So are you trying to have a chiral and anti-chiral part for this invariant?
No, it's a chiral part one.
So you are losing whatever anti-chiral part from your 4-dimensional theory as well when you do that?
What do you mean by 4-dimensional theory has much more than?
Sorry, Chris, can you use the microphone so people at home can hear you?
Oh, okay. I was just asking about the existence of like a quote unquote anti-chiral part for the 4-dimensional theory.
I don't think so.
Okay, so everything.
I mean, what they say it's enough to consider. Okay. So this is already surprising conjecture because Higgs branch is a very interesting geometric things, and you should be able to recover this geometric variety from this purely algebraic vertex operator algebra. Now, so I should remark that starting from 4D theory, you can construct 3D theory by reducing dimension by 1 by compactifying on S1, so physically compactifying on S1, and then it's known that the Higgs branch remains the same. And if you go to 3D theory, there's a so-called 3D mirror symmetry, where you can identify a Higgs branch with a Coulomb branch of the corresponding mirror theory. And this Coulomb branch has been defined by Nakajima and Braverman Finkelberg in many cases, and these are expected to have symplectic singularities. which is supposed to be a Lie theory for 21st century. So you can think four-dimensional VOA arising from four-dimensional theory as a certain affinization of these things. So you may think this vertex operator algebra as vertex operator algebra of 21st century. And this associated variety of vertex operator algebra in general is defined as a spectrum of certain Poisson algebra called Zuseitz algebra, naturally attached to a vertex operator algebra. And this Poisson algebra is in general not reduced, mostly not non-reduced, while a Higgs branch, which is again defined as a spectrum of a Higgs branch chiral ring, well, this one is reduced. So there's some subtlety between these things, but non-reducedness of this Zuseitz algebra actually good in the following sense. So because it's non-reduced, it makes sense to consider corresponding scheme, which I call associated scheme. And then it's conjecture by Rastelli that this associated scheme is already completely invariant of the four-dimensional theory. And I should remark that the associated variety or Higgs branch is not a complete invariant because there are many for this theory which has just point as a Higgs branch. But if you consider associate scheme really as a scheme, it distinguishes every four-dimensional theory conjecture. So using vertex operator algebra, you find some scheme, finite dimensional scheme, which cannot really reached from four-dimensional, three-dimensional theory, if you consider 4D, 3D corresponding. Okay, and so as I said, the map from 4D theory to VOA should be injected. So it's natural to ask what characterize the image. And so, of course, this is a very difficult problem because this is almost equivalent to defining four-dimensional theory. So I don't know the answer, but I can say a little about some of the property that image should have. And as I said, associated variety is a Poisson variety. So it makes sense to consider the symplectic leaves inside it by considering stratification by analytic Poisson manifold. And we call vertex operator algebra quasi-leaf if this associated variety has finitely many symplectic leaves. And physical consideration shows that the vertex operator algebra, if it comes from 4D theory, it should be quasi-leaf. So it's natural to ask what can we say about quasi-leaf vertex operator algebra. And here is our result. And if V is a quasi-leaf vertex operator algebra, then one can show that there are only finitely many simple ordinary representations. So ordinary representation means those representations whose character makes sense. Not only that, so as I said, character makes sense, and the statement that the character converges to the holomorphic function on the upper half plane, and also it's the characters satisfy a certain linear differential equation called modular linear differential equation. And this modular linear differential equation is an equation which modular forms satisfy. So in particular, space of solution of a modular linear differential equation is invariant under the natural action of SL2G. So, so this shows a certain modularity of character of ordinary representation, in particular vertex operator algebra itself. And the character of a vertex operator algebra is supposed to be Schur index. So this shows certain modularity of the Schur index of the 4D theory, which cannot be proved in other ways as far as no. And this modularity is important because notion of effective central choice is well defined, and which gives another there are two central choices in 4D theory, and this effective central choice is essentially another central choice. So this is one application of vertex operator algebra to physical theory. Okay, and it seems that the Schur index of 4D theory is always quasi-modular form, but I don't know how to prove such a statement. Okay, so let me show some example of quasi-Lie vertex operator algebras. So let's first consider the simplest case. Let's consider C2 is coordinate PQ, and we give just natural symplectic structure. And then if you quantize, there's a natural quantization of this symplectic manifold is so-called wide algebra. It is the algebra generated by this with this relation. And then you can consider chiralization or affinization by considering, so the natural chiralization is called so-called beta gamma system, which is generated by beta and gamma. So beta corresponds to Q and gamma corresponds to P. And the lambda bracket is given by this formula. So this corresponds to this relation. So in terms of Fourier coefficient, this means this commutation relation. So beta gamma system is just a wide algebra generated of infinity rank. And so this is from this defines a vertex operator algebra. And you can show that the corresponding associated variety as exactly C2 we started with as Poisson varieties. And you can play with this example a little bit more by considering the natural action of SL2C on C2, which is Hamiltonian. And so the corresponding moment map is given by this formula. And then corresponding co-moment map gives a Lie algebra homomorphism from SL2 to this Poisson algebra generated by PQ, and which is given by this formula. And if you remember, Q correspond to beta and the P correspond to gamma in previous construction, you can just replace Q and P by beta and gamma in this formula to obtain representation of a Kac-Moody algebra on the beta gamma system by this formula. And then you find that this has level minus one half. And so this generates a vertex subalgebra of inside the beta gamma system, which is isomorphic to the simple affine vertex algebra at level minus one half. And one can show that the corresponding associative variety is just exactly the image of the moment map of C2, which is a nilpotent cone of SL2. And because nilpotent cone it has finite many. So nilpotent cone, the Poisson structure symplectically here is just a quadrant orbit, and because nilpotent orbit has finite many quadrant orbit, this vertex operator algebra is quasi-Lie. More generally, you can consider vertex operator algebra associated with affine Kac-Moody algebra. So this, I think, Jethro explained last week, and so this is a universal one. This is not simple, in general, so you can take simple quotient, which we are interested in, and we denote by this by LKG. And associated variety of universal vertex algebra is just a G star, which has infinitely many symplectic leaves. But the same, if you consider simple one, it's contained in G star, which is G invariant conic. So this has chance to be quasi-Lis. When K is not rational, the level is not rational, then in fact, this universal one is already simple, so associated variety is G star. And on the other extreme, if in fact you can show that these two things are the same if and only if the associated variety is G star. And on the other extreme, there are cases when associated variety of the simple one is just a point. And this happens if and only if LKG is integrable. And this happens if and only if K is non-negative integer. So this is certainly an example of quasi-Lis vertex operator algebra because point is just one OB. But this is unitary, so this doesn't appear from a four-dimensional theory. So to obtain examples coming from 4D theory, we have to consider more general representation, such as -half at level -5 that appeared previously. And it's easy to see if this simple quotient is quasi-Lis if and only if the nilpotent associated variety is contained in the nilpotent cone. So in this case, associated variety is really analog of associated variety of primitive ideas of enveloping algebra. And so this happens when LK, this simplifying vertex algebra, is so-called admissible. So this is already explained in Jethro talk last week, so I will not explain too much. But it has, the point here is now the level has a rational value. So shifted level is positive rational number whose and the numerator is not so small. And if this is the case, one can show that the associated variety is the closure of some nilpotent orbit. And in fact, nilpotent orbit can be described explicitly as this by this kind of formula. So not all orbits appear, but this kind of orbits appear. And so I should say, so this is a from a infinitely many example of quasi-Lis vertex operator algebra. And now you can ask whether they come from four-dimensional theory. And they do come from four-dimensional theory, from Aguilar's double theory, if the level K is boundary admissible, which means that the numerator is as small as possible. And so I didn't explain too much, but this associated variety only depends on the denominator. So for each orbit like this, there exists a unique level which gives vertex operator algebra coming from 4D theory. And if you are familiar with modular representation theory, you find that this is quite similar to so-called restricted null cone that appear in modular representation theory. And in fact, you can show that the associated variety of admissible representation is a spectrum of a cohomology ring of a small quantum group of root of unity, where root of unity is described by this formula. So there's a well-known correspondence between quantum group and affine Kac-Moody algebra by Kazan and Lustig, but this correspondence is a bit different. because in causalistic correspondence K plus HX, the shifted level comes in the denominator of the exponent. And so this looks quite interesting. So it's natural to ask whether a further correspondence between representation of Heine-Kac-Moody algebra and small quantum group. And the answer is yes, but you have to consider quite wide representation. So we need to consider category of weight representation, which is not necessarily highest weight. And the statement is that the category of weight module of admissable affine SL2 is blockwise equivalent to the category of module of an unrolled small quantum group at the same root of unity. So this is rather a surprising statement because the category of weight representation does not have nice structure even for finite dimensional Lie algebra G. For example, if you consider SL weight representation of SL2, you don't find projective modules. There's no projective module. But the point here is you consider a representation as vertex operator algebra. So if you as long as you consider representation of simple affine vertex algebra, then category becomes very nice and has becomes the highest weight category and becomes equivalent to the category of module over small quantum groups, blockwise equivalent. And so far we can prove only for SL2, but we conjecture that the same is true for any simple Lie algebra. Yes?
So what does this blockwise mean?
Blockwise means, actually there are only two blocks of small quantum group. And this category of weight module has two kinds of blocks also. And if each block is equivalent to.
But have more blocks.
They will have more blocks. And so this work was motivated by two things. One thing was work of Klutik and Ridout, who conjectured that this category of weight module should have a modular tensor category structure. So this is a shadow of such statements because the category of unrolled quantum group has a modular tensor category structure. And another motivation is again for the 2D duality. And according to the work of these people, when this admissible representation comes from 4D theory, then the semi-simplification of this modular tensor. So this modular tensor category has infinitely many simple objects. So this is quite wide modular tensor category. But if you consider semi-simplification by quotient out negligible modules, then it should become a nice modular tensor category, and it should coincide with modular tensor category associated with the Coulomb branch, which is another branch of the 4D theory. I have not talked about too much about because Dupé, I think Dupé is going to explain a little bit, maybe. Okay, so there are much more things to do in conclusion for representation theory of admissible representation, purely in representation theoretic perspective and also in connection with modular tensor category and with also 4-dimensional Coulomb branches, which is certain Hitchin modular space. Okay, there are several ways to construct 4-dimensional theory. And one technique physicists use is so-called F theory. So they start with so-called isotropical elliptic fibration and apply this F theory to obtain 4-dimensional theory. And if I understand correctly, the resulting 4D theory only depends on the singularity of the elliptic fibration. And the singularity of elliptic fibration is classified by Kodaira. And according to him, singularity are labeled by simply laced member of so-called Deligne exceptional series, which is a series of real algebra of this type. So except for G2 and F4, which is non-simply laced, you have corresponding for this theory. And what we did with our model is that if G is one of this Deligne exceptional series, then associated variety is isomorphic to the minimal nilpotent oblique closure. And this is new. This is not admissible because when G is simply laced, because this number is a negative integer. So this gives a new family of quasi-Lie vertex operator algebra, and this VOA is exactly the VOA coming from the 4D theory obtained by F theory. And this is the very first example of the 4D theory of the 4D 2D correspondence. And so this was actually our first, this was starting point of this project. Because we studied this vertex operator algebra by different motivation, and it turned out that this coincides with the one appearing from this theory. Okay, and the other interesting symplectic variety, for any nilpotent element, you can consider corresponding SL2 triple. And you can consider corresponding slowly slice, which is transversal slice to any J orbit that appeared in Daniel-Stokes and Desraux-Stokes. And you can consider intersection of this slowly slice with nilpotent cone, which are known to be hypercoherent. And this one is called nilpotent slowly slice. The most famous case is a case when G is simply laced and the nilpotent element is subregular. And in this case, this intersection has simple singularity of the same type as G at this nilpotent element. But you can consider this kind of thing for any orbit and any nilpotent element yeah. And the statement is that this nilpotent slowly slice appear as the associated variety of so-called double algebra. So I will not explain too much. As long as the orbit closure appear as that of the simple affine vertex algebra. In particular, as an admissible level, this kind of slowly slice do appear as associated variety. And this double algebra appear from 4D theory, again, the level, if level is boundary admissible. So this gives another interesting family of vertex operator algebra coming from 4D theory. And they have very rich representation theory, and they are yet much more to be done.
Sorry.
Yeah.
There is no assumption on the level for this sequence.
This as long as the orbit closure appears. Yeah. It's stored. Ah, okay. So there's another. Oh, I have pointer. There's another popular symplectic singularity that appears when you consider natural action of symmetry group on Cn. And this action induces action on cotangent boundary to Cn, which preserves symplectic form. So you can consider corresponding quotient by considering spectrum of invariant ring. And so this has singularity. So this singularity can be resolved by considering Hilbert scheme of endpoints in the plane. And Kashiwara and Rukie constructed a sheaf of algebras on the Hilbert scheme, which quantizes this symmetric powers of C2. And the global section of the sheaf is equal to the spherical part of the rational Tyrrhenic algebra associated with Sn. So it's tempting to try to chiralize their construction to obtain vertex operator algebra, but naive affinization of their construction does not seem to work because of the existence of obstruction of constructing sheaf of vertex operator algebras. But then 4D, 2D duality appear, and they seem to expect the existence of sheaf of vertex superalgebra on Hilbert scheme on C2. So the point here is you have to consider sheaf of vertex superalgebra, not just vertex algebra. And this slight difference makes miraculous difference, and it cancels. If you add super part, it miraculously cancels the obstruction. And so this is not yet theorem, but our statement is that there exists a natural sheaf of vertex superalgebra on Hilbert scheme, whose associated variety is the symmetry of C2. So this is a natural affinization of Kashiwara-Rukie construction. And if you consider n equals to 2 case, you obtain as global section the small n, essentially its global section is small n equals 4 superconformal algebra, a tensor with a certain free field. And this, so nice thing about sheaf construction is that you can obtain free field realization by restricting the sheaf on open, affine open set. So this construction automatically gives a free field realization of the global section. And this free field realization is the same as Drazen's realization of the simple small n equal 4 superconformal algebra. So this is something we are very happy. Okay, and let me explain one more example, which is class S theory. So as I said, there are many ways to construct four-dimensional theory. And one can start with even higher dimensional quantum field theory, which has 6 dimensions. And then you can restrict this 6-dimensional theory, compactify, physicists say they compactify on punctured Riemann surface to obtain 4-dimensional theory. And the resulting 4-dimensional theory is parameterized by the punctured Riemann surface you used to compactify. And also a semi-simple group, which is attached to a 6-dimensional theory, which is called flavor symmetry group or gauge group. So you have a nice family of 4-dimensional theory parameterized by pair of punctured Riemann surface and semi-simple group. And you can ask what is corresponding vertex operator algebra. And so you can also ask what is the corresponding Higgs branch. And the Higgs branch of this class S theory is described in terms of 2-dimensional TQFT, whose targets are holomorphic symplectic varieties. So in usual 2D TQFT, targets are vector space. But in this TQFT, you replace vector space by symplectic varieties. The target category of Moa Tachikawa, so let us call this TQFT Moa Tachikawa 2D TQFT, is a category. So I call this a category of symplectic variety, but that their objects are not symplectic variety, but semi-simple groups corresponding to this flavor symmetry group. But And the morphisms are given by symplectic varieties satisfy certain conditions. And the Higgs branch of the class S theory are the symplectic varieties that appears as the image of two Bodhism, which are morphism of this category, and they are called Moatachika varieties. So we use just as usual correspondence. So if you want to find more Higgs branch for P1 with 3 punctures, then this corresponds to two Bodhism with same genus with 3 boundaries. So number of 3 punctures and number of 3 boundaries. And then how about vertex operator algebras? So according to Beem et al., so vertex operator algebra appearing from this class S theory has fancy name, and they called chiral algebra of class S. And chiral algebra classes, according to them, have the similar description in terms of 2D TQFT, but you replace a symplectic variety by vertex operator algebras. So in Moatachika TQFT, targets a semi-simple group and morphism are symplectic varieties. And in this TQFT, objects are the same groups, but morphisms are given by vertex operator algebras, satisfying certain conditions. And a statement is that such a 2D TQFT indeed exists, and it's characterized by this condition. So first condition just defines a correspondence between objects. So S1 goes to this group, Weber symmetry group, and the cylinder goes to so-called CDO at critical level on G, and the cap goes to the Dunning-Sokolov reduction of CDO. The statement is that this uniquely characterizes this functor, and moreover, if you consider associated variety of the VOA that appears as image, it coincides with the Moatachika varieties. And so this, as I explained. So the number of functor means number of actions of Heine-Kotzebue group. So if there are 3 boundaries, there are 3 commuting actions of Heine-Kotzebue algebra. And if it's genus 0, then one can show that the image. I didn't impose any simplistic condition, but it automatically follows that the image is simple and conformal with the correct central charge. And one can compute the character, and which turned out to be closely related with multiple Q zeta functions values. So they have very interesting character. And the last statement of the theorem proves the conjecture of Beem last. Because of the uniqueness statement, this must be the vertex operator algebra coming from class S theory. So this proves a conjecture of Beem last theory on the coincidence of appearance of Higgs branch as associated variety. So let me show some example. So simplest case is the case of SL2. So what is image of pair of points for associated Higgs branch? So this is just a 3 tensor product of C2, and the corresponding vertex operator algebra is just a beta gamma system associated with this symplectic vector space. But if you consider increase the number of punctures or boundaries by 1, you get more non-trivial one. What you find is minimal nilpotent oblique closure in D4, which has singularity. And the corresponding, so the reason why D4 appears is that so this should have 4 commuting action of SL2. And you find 4 commuting action of SL2 if you write a finding in the. And the corresponding vertex operator algebra is the simple affine vertex algebra associated with the D4 at level -2, which is the same that appeared in the case of F theory. The Frobenius relation of two Bodhism is assured by the triality of D. And the isomorphism between Higgs branch and associated variety and more-attached variety reproduce the previously stated result with Amuro. And associativity, or the compatibility with the composition, gives some isomorphism between symplectic variety and vertex operator algebra. And for symplectic variety, this is a statement like this, which is a ADHM construction of minimal nilpotent of closure. And for vertex operator algebra is this kind of isomorphism. So the compatibility with the composition of two bodies gives a family of non-trivial isomorphism of symplectic variety and vertex operator algebras. And for SL3, as you can guess, more-attached variety for 3 puncture is minimal nilpotent of closure in E6, where you find 3 commuting action of SL3 on Dynkin diagram, affine Dynkin diagram, and the corresponding vertex operator algebra is the affine vertex operator algebra associated with E6 at level -3. So -3 is a critical level of SL3. And in general, neither of these has simple description, and these are a completely new family of symplectic varieties and vertex operator algebras. And so as I said, for a cylinder case, it's CDO on G at critical level. And it's known that the category of GT equivariant module over this CDO is equivalent to the category of affine Grassmannian, a critically twisted D module on the affine Grassmannian, which has very interesting representation theory. So, and you can think chiral algebra of classes a generalization of such VOA, and I believe they should have very interesting representation, which yet to be investigated. Okay, thank you very much.
Some time for questions, please. Question.
So you said that the functor V from 4D to 2D is not essentially surjective, but it should go inside the quasi-Lie vertex algebras. Do you expect that if you restrict the codomain to this quasi-Lie vertex algebras, maybe with some more conditions, you can get surjectivity?
No, because only for admissible cases only. So there are many admissible representations which are quasi-Lie, but only if you fix denominator only, there only exists one P that comes from 4D. So other one does not come from 4D theory. So this should something to do with 4D unitarity, but
some more questions?
Yeah, so my question is, so you mentioned, it's a similar question. You mentioned in the beginning that it's conjectured now that the map from the 4D to the associated scheme is injective. But of course, we know from VOAs to that it's not injective. So that's taking any VOA, not in the image of the 4D maps.
Sure.
So now if you start from an associated scheme that comes from 4D, there should be some kind of canonical pre-image in the VOA.
Right,
we have some, I mean, this is of course very philosophical question, but we have some kind of idea how to get this kind of
there
pre-image.
should be the conjecture that there should be so VOA coming from 4D theory should have nice filtration, which is different from Lie filtration. And the associated grade should be recovered from this associated scheme. So there should be a way to naturally quantize the jet scheme of the associated scheme.
Oh, yeah. Yes, thank you.
Chris, did you have a question? No. Question down here. Pass the mic over.
Thanks. So in this very first case which you had with beta gamma systems, can we I mean, maybe it's naive. Can we in some sense see this Poisson variety in the representation theory? Or maybe can you tell us what the mirror is so we can see that this X string is like this? Or I mean, can I somehow see the C2 representation theoretically?
It's a conjecture of Thomas and Guyot and Costello that you can restate mirror symmetry, 3D mirror symmetry in terms of vertex split algebra. So this C2 coordinate ring, this should be X algebra of the mirror.
And what is the mirror?
Ask Thomas.
Okay.
Any more questions?
You mentioned this family of vertex algebras related to Kodaira's singular elliptic vibrations in 2 dimensions. Do you have any expectation like that some enumerative invariants of those surfaces factor through the vertex algebras?
I don't know the answer, but there is one interesting observation by Tachikawa. So this number is a global invariant of this elliptic vibration in the sense that this elliptic surface can be described by, I think C2 times elliptic curve by and G by this action of before. It seems that this vertex operator algebra has some global property of the corresponding elliptic surface. But yeah, I don't know.
Any last questions? If not, let's thank Tomoyuki for a fun conference.